this problem, we've got a crate with a mass of 100 kilos getting pulled by a force P of 500 newtons. So this is 500 newtons. And the coefficient of kinetic friction between the crate and the ground is 0.2. So I just added that on. So it's asking us how much work's done by the force P. What's the net work done by all the forces when it's pulled 2 meters, and the velocity of the crate after it's pulled 2 meters. So when you start to get to these problems that got multiple forces, it's important to draw a free body diagram of the object and make sure you're putting all the forces onto that free body diagram. So we'll assume this thing's homogeneous, so the center of gravity is going to be right in the middle. I'll just move this down a fraction. So we've already got, I've marked on that force of 500 newtons. We've also got gravity acting on this. So we have got, well, this is a primary force, we'll do that in blue as well. So this force W equals mg, which is equal, just figure it out now. The mass was 100 kilograms, so it's 100 times 9.81, which is equal to 981 newtons downwards. So it's going downwards. We're going to have a reaction, a normal force. And there's no other vertical forces acting on this object, so that normal force must be equal to the weight, which is equal to 981 newtons. Then we've got friction. Oops, we've got friction acting like so. And the friction, let's just calculate that at the side. Just move my diagram to the right hand side. So our friction is equal to coefficient of kinetic friction times the normal force, which is equal to 0.2 times 981, which is 19.62, I think. 0.2 times 981, 196.2, yeah, that makes sense. 196.2 newtons. So let's just add that to our free body diagram as well, 196.2 newtons this way. Now, and then it's going to move 2 meters. So this, maybe we could say T1. Or we could just say, I don't think we need to. I was just thinking, do I need to show that? We could just let's just add that on. It's going to move 2 meters. You don't have to do this in your working, but it's going to end up here. And that distance is 2 meters. So I guess this is the first part is at T0. I'll just make sure I'm showing what direction it's going in. It's going 2 meters that way. This is T0. This is T equals T1 times 0 and time 1. Okay. So the first question is asking us how much work is done by the force P after the crate is pulled 2 meters. So this is just the work done by this force, and so the definition of the work done by a force, work done is equal to P times displacement in the direction of P, and it's going in the direction of P, so it's going to be positive. This is positive 500 newtons, it's going in the positive direction as well, so it's just going to be 500 times 2, which is equal to 1,000 joules. 1,000 joules, or 1 kilojoule, you could write that as if you wanted to. That's the answer to that. But what we have to start being careful about is when you got more than one force acting, you need to think about what the net work done by all forces on the crate is after it's pulled 2 meters. And so when we're figuring out the net force, well, there's a couple of things we'll pick out from this, and we'll talk about these a little bit more soon. But the first thing is that you've got gravity acting downwards, but the object does not move in that direction. So gravity is acting downwards, but the object is moving horizontally. So the work done by this force is zero. The displacement in the direction of that force is zero. And so we don't have any work done by that force. Similarly, the normal force, it's in the vertical direction, but the object is only moving in the horizontal direction. So there's no work done by the normal force either. But there will be work done by friction, because it's moving in the horizontal direction, and friction's in the horizontal direction, and they're opposite. So it's going to be negative work done by the friction. So what we could say is the net work done, which we can write as the sum of U, is going to be equal to, so we're going to have P times the displacement in the direction of P minus mu K, I'll just write it out in full, mu K N. Now it's a bit, let's just put it as negative. So it depends how you write this down. I'm writing delta S, let's just write it down like so, but we're kind of taking the magnitude of delta S here. Really, this is negative, delta S is positive, so we're taking them all together, we're getting a negative for the whole thing. So it's negative work is getting done by that. So we've already calculated P delta S, that's 1000, minus, we calculated the frictional force up here, 196.2 times delta S is 2. So the net work done is 1000, take away 196.2 times 2, which is equal to 607.6 joules. So the net work done, for the answer to this question here, the net work done by all forces after the crate is pulled 2 meters is 107.6 joules. Just writing out the answers to the question. And then we'd underline those. So the next part, what's the velocity of the crate after it's pulled 2 meters? So what we have to think about here is the fact that this force here has, as it travels certain distances, doing a certain amount of work, but some of that work is to overcome friction. So we're losing energy due to friction. And so you're doing a bunch of work. This is working against you. It's the frictional force is working against this force when you're moving in this direction, and friction always works against the direction of motion, so it's always negative, so it's always stealing energy. And so when we calculate what the kinetic energy of this is, when we've got friction acting, it's the net work done by all the forces that matter. And so therefore we can write the equation half I'm just thinking whether I write this in full. So half mv1 squared. So the change in kinetic energy, half mv naught squared. So that's the change in kinetic energy. We can just write that as a half initial velocity, the final velocity squared, take away the initial velocity squared, is going to be equal to the net work done. Now we'll assume this was at rest to start with. It doesn't really tell us in the question, but let's assume it's at rest. I'll add that later. So V naught equals 0. So therefore half mv1 squared is equal to 607.6 joules. Therefore V1 is equal to square root of, now do we have the mass? We do. So it's going to be 2 times 607.6. So I'm just multiplying both sides by 2 to get rid of the half. And then I need to divide by the mass, which was 100. And then I take the square root because that's V1 squared. So we want V1, so take the square root both sides. So it's 2 times, square root is 2 times 607.6 divided by 100, which is equal to 3.49 meters per second. So So the velocity is equal to, at 2 meters, equal to 3.49 meters per second. Hopefully that makes sense. Now again, we could figure that out using statics and so on. So we could find the net force and the acceleration, and we could do a quick check on that. Might do a quick check myself. I won't subject you to it. So we could figure out the net force is just 500 take away this force, divide it by the mass, you would get the acceleration of this thing, and so then we could use the equation for velocity with distance to find the velocity after it's traveled 2 meters. So I'll do a quick check now and I'll put it in the working, and you can have a look at that in the MyUni.